I'm not going to teach you C and C++ development because most people already know how to do that. But what I will teach you is some of the issues we have to deal with in the new multi-core environment that we're in. So let's talk a little bit about the history. About 10 years, from 93 to 99, the CPUs were getting faster and faster. The clock speeds were getting more and more. And if you follow the trend and just drew the line up to today, we should be having 10 gigahertz CPUs. But last time I checked, there's no 10 gigahertz CPUs. So what happened? What happened was basically there was heat. They got too hot. The CPUs got too hot to run. So you have bigger and bigger fans. There was power. They take more and more electricity. So they ran hotter. And getting out to memory was much slower. And so what did people do? The chip designers decided they're going to make something called multi-core systems. So they took one CPU and they replicated it many times. And so you have one chip, but that chip has multiple cores on it. All the major vendors are doing it now. Sun, Intel, IBM, AMD. Everyone who's making a chip is making a multi-core chip. Now, what does this have to do with C or C++? Well, as developers, before you could write some code, and when you bought your next system, it would just run faster because the system ran faster. But now, with multi-core systems, the clock rates are pretty much where they're going to be, somewhere between 2 and 3 gigahertz. Maybe if you're lucky, maybe 3.5 gigahertz, but you're in the 2 and 3 gigahertz range. So now when you buy a new system, you're not getting a faster system. What you're getting is more cores. And so the problem changes from just buying a new system running faster to figure out how to write code to take advantage of all those cores that are out there. So there's many different languages to do that, and one of the things that you do, there's many different models to do that. Let's talk about the models first. So at the very bottom, there's the different multi-core chips that are available. There are companies like Sun and others that put those chips into bigger systems. I think I asked earlier this morning if you were at Chris Arms's keynote talk, how many people bought a laptop in the last year or two. And many people raised their hand. All those are multi-core systems now. So more people are putting those chips into systems that are available. You need an operating system to run those systems. OpenSolaris. Solaris happens to be a very good one because two of the things you need in an operating system is stable threads, a multi-threading environment that is good threads. And second thing, you need a good scheduler to schedule those threads. Solaris and OpenSolaris has a history for about 15 years of being a multi-threaded operating system. So it's something that they work a lot of problems out over the years of Solaris and OpenSolaris. On top of that, there's models of applications, software models. And so a few of them are here: virtualization, whether it's VirtualBox or Zen, VMware, some way to drive those cores more by running things in parallel. Another model is what you have in containers, any kind of an app server, web servers, Glassfish being one example. You replicate your applications, or you have an app server that's serving multiple application requests that are coming in. And a third way that's probably a more traditional way is just having threaded code, multi-threaded code. And so I'm going to talk about in the C and C++ space, this last multi-threaded approach is the one that typically most people will do in C and C++. So the majority of this talk will be talking about the threaded applications running on top of these multi-core systems. So when you write code, you're solving a problem, but you believe you understand how the computer works. There's some behavior. When you write a line of code, you expect some behavior for that line of code. And you expect that behavior because you're familiar with the system you're writing for. In multi-core systems, they're very new, and people are not familiar with how those systems behave. And so when you write a line of code, it might behave very differently in a multi-core system than in a regular serial system. Second thing is design choices. You might choose a particular algorithm, a particular data structure, and you implement it. If you find out that the choice that you made doesn't lend itself very well for a multi-threaded application, it's very difficult to go back and re-implement or change your design after you've already implemented and you're testing and doing tuning of your application. So there's a lot more thought that has to happen up front when you design your algorithms. Worrying about global variables, much less use of global variables, Having the notion of objects, C++ makes this a little easier. You can contain the data within the object. In the C world, it's not quite the same. You have structures, but structures are frequently shared across many different routines. That sharing of data is a very difficult thing to get right in a multi-core environment. And there's lots of tools that are around. There's tools you can purchase, new tools, or there's tools you probably have already that you're familiar with, or I'll talk about some of the ones that Sun offered to help get this right, because it's a very difficult problem. Writing the code correctly, debugging it, tuning it, getting the race conditions, the data race conditions, etc., is all difficult problems to get right. So I'm going to talk a little bit about some of the tools that Sun has. I won't go through all of these, but just covering some of the highlights. We're going to look at it as three categories. There's develop, verify, and tune. And on the develop side, if you're doing C++, it's the compiler. Right? Your compiler is your friend. It's the majority of what you do when you're writing code. Sun has two features that it's very particularly proud of in its compiler. Number one is because we also make hardware, we make sure that the compiler generates as good as code as possible. And because we make SPARC machines and Intel machines and x86 machines, we want to make sure the performance on all three of those platforms is very good. So we have very sort of world record setting compilers. Secondly, because of the multi-core problem, it's very difficult to write threads on your own and get the threads correct. So of course you can. We support different threading models, but we also have an option in our compiler to automatically generate the threads for you. And I'm going to show that in some slides. Under the verifier, we have a debugger, of course. Everyone has debuggers. Debuggers are very much aware of threading and multi-thread issues. When you run our debugger, you can get access to all the threads and all different thread data. Something called the Sun Thread Analyzer, which I'll talk to you about briefly here, but there's a talk I'm giving tomorrow that will go in a lot more depth about the Thread Analyzer. This is a relatively new tool and something that will help you find data race conditions or deadlock conditions in your code. Two of the worst problems you get when you're doing multi-threaded programming. And then in the tuning area, we have a performance analyzer and something called Delight. Chris and other folks talked about dtrace, which is a technology in the operating system. And Delight is a tool that sits on top of dtrace that gives you a way to get better insight into what the operating system is doing in support of your code. So let me go into some of the details here. So first off, what do we have? In our compiler, we have the ability to automatically generate threads. So if you have serial code today, the code that you have in any application, there's an option we have in our compiler called auto-par. And auto-parallelization, essentially, is what it is. And so if you have a code that looks kind of like this, there's a simple nested loop. You have an inner loop and an outer loop. And this is just a matrix addition going on here. But it could be any activity inside the loop itself. There is an option in our compiler called auto-par. You give the compiler that option. And the second option I have here is called loop info, which is really something that tells the compiler, talk back to me. Tell me what you're doing with my loops. So you can leave the loop info one off, but in this case, it tells you what it did. And here you see the first line of output says, I was able to parallelize the outer loop. And in the second loop, it comes back and says, I didn't parallelize the inner loop. And the reason why I didn't, because it wasn't profitable enough. There's an overhead in setting up threads, and that overhead to fork the threads, have the work done, and then join them back together again. There's an overhead associated with that. And so if the overhead is more than the actual computation itself, there's no point in doing threads in that case. And so the compiler was able to determine in this case that the overhead versus the computation, it wasn't a good trade-off. So it didn't bother doing the threading, auto-parallelization of the inner loop. So a very simple example here, what the compiler will do is generate two kinds of code for you. It always generates a serial path, and then it will generate a multi-threaded path. And you control the number of threads that get run by a shell variable. And so here you see, you run it by default, it's the serial path. And this particular loop, because of the size of the data, took about 38 seconds. And then if I set the shell variable to 2, so now I have parallels 2 and I run it again, it drops down to, what is that, about 22 seconds. So you shaved about a third, by using 2 threads, you shaved about a third off of this particular computation. It multi-threaded the code for you, and it cut your execution time by about a third. Now, there's nothing special about 2. You can set the number of threads to 4, or 8, or 27, or any number you want. At some point, there is a fall off where you have so many threads running that you can't run them all efficiently. And so sometimes you need to sort of experiment a little bit to see what the right number is. In this case, just putting it at 2, you'll get a third off. If you set it at 4, you won't necessarily get a half off. If you set it at 8, you won't necessarily get 2/3 off. You need to play with the number a bit. But this is a very easy way to just take the code you have already, take the tool you have, your compiler you have already, and just try the option and just see if this helps. So kind of get your feet started in the multi-core area. That example I showed you was a very simple two loops, kind of made up fake example. But what we did was we took there's a benchmark called the spec benchmark. We took the spec benchmark that has integer and floating point operations. And these are about 12 or 13 programs that are in the spec floating point operations. And there's 2 bars there. The first bar is with single thread, no autopar. The second bar is with autopar option added. And so you can see in some cases, maybe the second, third, fourth bars, it's about equal, not much of an improvement. But you see other cases like the first, and maybe the fifth or sixth over that are very big improvements. So the average improvement across this is about 16%. So you might see something in your code that could be 50%, you might see 3%. But in some cases you'll see 0. There's a couple of examples here where there's no increase whatsoever. But if you want to get sort of started with multi-threading your application without getting into all the work and the hassle of multi-threading, just using the compiler options is a good first step to get going with it. Another thing that we have in the Sun compilers is something called vector support, or vectorization. And most compilers have this, but this is just another way of sort of pulling some more performance out of the compiler. So this isn't quite the same as threads. This is issuing a single instruction and having that instruction run on multiple pieces of data. So sometimes you hear SIMD as the acronym, SIMD, SIMD. And what SIMD does is very good for processing vector or matrix information. So you write code like what's on the left. Here's a loop here where you're simply doing some array multiplication. And what the compiler will do is see that and say, oh, these elements are distinct. So in one loop, I can in fact process 4 elements of your array. And so the compiler generates code that looks more like what's on the right-hand side. So your loop is cut by a fourth, and each iteration through the loop is doing 4 elements. And so, in fact, if your loop gets done faster, your code will ultimately run faster. Not quite using threads, but the same idea, using some of the advanced processor techniques to get faster code out of it. Again, it's a compiler option, so you need to tell the compiler, I want to try this. So it's the X vector equals SIMD option here. Again, we did this and many other optimizations with some of the benchmarks, and we compared what we had against GCC. So I think everybody either familiar with or has used GCC, myself included. And so if we use GCC as sort of the baseline number, we measured the numbers against GCC, and then we measured it against our own product, which was 12, Studio 12, and our new one, 12 Update 1. And we see these kinds of improvements. So from significant numbers, the percentage improvements are compared to the first number, the first bar, GCC. You'll see, again, the left side is Spark, the right side is Intel x86. And the 2 groups of bars, the first one is predominantly integer-based applications, and the second one is predominantly floating point applications, the spec-int and spec-fp types of applications. So you can see on the floating point in particular, the Sun tools do quite well. And it's because of our background and our history in producing tools for large server environments. So I mentioned the thread analyzer. So if you're writing multi-threaded code, either explicitly by using POSIX threads, or perhaps implicitly through OpenMP. Anybody heard of or use OpenMP? Show of hands. 1, 2, 3. Okay, good. A couple of folks. So OpenMP is another technique. And I'll talk about this a little bit more in my talk tomorrow about being able to introduce threading into your application without having to rewrite the whole application. If you have an existing application and you want to change it from serial to parallel, OpenMP is a way that you go in and you can selectively find the hotspots and just parallelize the hotspots of code without changing your entire application. However you do this, if you have threads in your code, you need a tool to help you find where the thread deadlocks might be. The thread analyzer, when you fire this thing up, it will show you, when you run the application, it checks all of your memory references. And if it finds that there's 2 threads accessing the same element of memory, it will report that. And it'll show this as a race condition. Here it's saying the shared variable is being accessed by multiple threads. If you look at the very next tab, the next tab is called the dual source panel. When you click on the dual source, it actually shows the lines of code. So the first tab simply says, I found races. The second panel will show you the line of code between the 2 threads where the races occurred. So in this particular case, it's saying that it's seeing a write, 2 writes here, both writing to the same variable. And as a result, you have 2 threads writing to the same variable. One is going to clobber the other in some way. Now, it doesn't tell you how to fix it, but it does point to the line of code that you have to go and work on in your application to get it to be thread correct. The other tool we have is the Performance Analyzer. The Performance Analyzer is a tool that lets you measure how well your application is running. It particularly can also measure in a multi-threaded environment how well your application is running. Most people, I think, are familiar with profiling, prof or gprof. So the first tab in here looks very much like a gprof type tab. You click on the functions and it'll give you a list of functions, the most expensive down to the least expensive. So places where you might want to go and look at for tuning. You can go to the actual lines of code by clicking the source tab. And in the source tab, you can see which line of code is the most expensive line of code in your program. And then there's a timeline tab. And in the timeline tab, what you see is down the left side is the threads. So if you actually have a program that has multiple threads, each one of those lines is one of the threads of your program going across the x-axis is time, and then the y is the multiple threads. You can click on any one of those. They look like there's graphs with different colors. The color combinations are in the bottom right. It tells you what function or what routine is actually getting access to the call stack on the right. And you can click on any one of those, and it'll take you to the source code and give you more information about that particular piece of that thread's application. So you get the big picture of the thread analyzer. The performance analyzer will give you each thread's execution line, and you can click on the elements within the execution of that thread, and you can get information about what's going on with that particular thread there. Delight. The Delight is a tool that is a new tool that we have introduced. So in the Open Solaris, Chris Arms this morning talked about dtrace. Perhaps was there a dtrace deep dive, I think, earlier today too, that Peter was giving, perhaps? Dtrace is a great technology in the operating system to track what's going on with very little overhead. Now, from a developer point of view, you need to know a lot of what's going on, what probe points are available in the kernel to get that information out using dtrace. With the Delight tool, what we give you on the left side is a palette of routines that are sort of pre-packaged dtrace scripts that look at things like perhaps file I/O or execution, process time, process execution time. There's about 12 or 15 of them in there. And you drag and drop them into the center portion, and then you start running your application. And what happens is, as the application is running, it's collecting the dtrace information and showing that in a timeline across the line. So it traces events that are happening live in your application. And again, if you can click on those graphs, those links are hot, you can then get to your source lines of code. So what this tool does is it gives you a way to see a system event that occurred and trace it back to the line of your source code that caused that system event to happen. There's a file read or a file write. Again, multi-thread aware, so you can get multiple threads with this as well. Most people, how many people are familiar with NetBeans or use NetBeans? Yeah, many. NetBeans has if you go to the NetBeans website, there's a bundle that supports C and C++. And so if you get the NetBeans IDE and you download the C++ bundle, it's what we use in the Sun tools. So what this is essentially the NetBeans wrapper around the Sun compiler, debugger, thread analyzer, performance analyzer, etc. So you get all the things you would find in the NetBeans environment. So at the top left, you have the project system. Because we're talking about C and C++, there's a class navigator, so you can see what the different classes are in C++. There is what you would expect to find in any kind of a modern IDE. There's a hover expression evaluation. So you can either get it by hovering the cursor. In this case, it's not an expression, but actually showing you the data types. In the debugger mode, you would get the variable evaluated at the time. There's a bunch of panels at the top that are kind of grayed out right here, but that's when you're doing it in debugging mode. So you can do many different options for debugging. Again, all multi-thread, multi-core aware. Language highlighting, what you would expect to find in any language, or language editor highlighting. And then makefiles, unlike Java where you have Ant scripts, here you're talking about makefiles. And so there's makefile wizards and makefile imports. So all of these tools together, we're talking about basically getting performance, getting parallelism, and hopefully making you more productive with these multi-core systems that are out there. There's different platforms that it runs on, and so clearly many people do development on Solaris, but there's also many more that do it on Linux. And so we support various flavors of Linux as well, not just Solaris and Open Solaris, but these tools with the compiler options and the auto-parallelization also work on Ubuntu, work on SUSE and Red Hat. So you can get them for Solaris, you can get them for the other platforms as well. Where can you get them? So on the Sun site, developer Sun.com. The product that Sun sells is called Sun Studio. So if you go to that site /Sun Studio, you can download them and get them there. Okay, so I have a simple program here that creates prime numbers. Everyone knows what a prime number is. And so this is a program that just creates a number of prime numbers between any two numbers. So I just programmed it to be 1 to 3 million, just to see what it works. Let me just make sure it's all clean here. We'll do a make clean. Get rid of all that. And we'll do a make. And what it's going to do is generate, it's building, I have 3 different versions of the program. One version is a serial program, which is how you probably would write it to begin with. I have one version which is using OpenMP, which is the sort of incremental way to parallelize your code. And one program that I used, Autopilot, to automatically parallelize the application for me. So it built all of these 3 versions right here. So if I look at the serial version, let's just run that and see what it says. Okay, so there's 216,816 prime numbers between 1 and 3 million. Right, so that's not too hard. Let's time that. It took, what, a couple seconds, maybe 2-3 seconds? 5 seconds? Okay, 5.1 seconds. This is a little bit older. This is about a 1.5 old laptop. It does have a dual core in it. It's an Intel dual core system here, so there's 2 CPUs. Now, if I run let's time actually I have 2 versions of OpenMP, a broken one and a fixed one. Let's run the fixed one. 3.3, 3.4 seconds. So there's actually only one line of code, 2 lines of code difference between these two. The serial version is how you would write the program to begin with, and the OpenMP version indicates that I want to parallelize the main loop, and I want to protect a particular critical variable. So I added 2 different lines of code, and by running it with OpenMP, I was able to shave off about 40%, from about 5 seconds down to 3 seconds. So that's a pretty good time. Now let me just try the same thing with the AutoPAR. I have the AutoPAR version over here. Wow. That's ran very fast, but it's not there. Let's see what we have. Let's see which one that is. I'm not sure. Go look at the makefile. I haven't looked at this in a while. So let's see what we have. AutoPAR is AutoPAR. That's easy. So I'll make AutoPAR. All right, so now here we see I gave it the AutoPAR option. Let's scroll this up a bit. So here you can see I gave it the, step down. So I gave it the AutoPAR option, and the loop info says, tell me what you did. And so we looked at the outside loop, and it says, I can't parallelize the outside loop. And the reason is because it has multiple exits. So it's not a very clean algorithm. I kind of was doing some checks, and I would continue or did it go to. I just wrote it quickly, so it's not very clean code. The second loop it found, it said, I can do that one. I parallelized that one for you. So now I've got multiple threads for that loop. And then the third one, it said, I can't parallelize that because there's a function call in the middle of it. And I don't know whether the function call is thread safe or not. So this is the question about, can I just run it on a complex code? If there's any complexity, it's very conservative. And so if you call a function, it doesn't know whether that function is thread safe. And so it says, I can't tell what that function is, so I'm not going to parallelize that. So I have 3 loops in here. The first one said no, the second one said yes, the third one said no. And then it built the AutoParallel version. So because I had other 3 loops, but only was able to do 1, I probably don't expect to see a whole lot of improvement here. But let's see what it does. So not a whole lot of improvement. The other one's about 5.1, this is about 5.1. So not a whole lot of improvement here. The key in this particular algorithm, and I'll show some of the code, I could show some of the code, but the third one is the work routine. I'm calling the routine that checks whether it's a prime number or not. And since it doesn't know whether that's thread safe, that's the real work routine. Without threading that routine, you don't really get any benefit from the auto threading. And so here the AutoPAR didn't help. OpenMP, I knew that routine was safe, so I put the line in there saying you can parallelize this loop. And so I manually went in there and I added that line, so adding 1 line of code. And that gave me the speed up from 5 seconds down to 3 seconds. So AutoPAR is good when it's good, and when it's not, OpenMP helps to do it incrementally. And then there's the POSIX thread. Actually, I have a POSIX thread version in here as well. Let's just run that and see what the time is on that. Pirate time, where is it? T-fixed. Okay, so 2.8. So remember the numbers, about 5 seconds for the first one, serial, about 3 seconds for the OpenMP, and 2 seconds for the parallel code. Now let's look at the difference in lines of code. If I look at the serial version, just look at the lines of code here. What's wrong with this? Oh, I missed that. All right, there we go. So 45 lines of code there. If I look at the OpenMP fixed version, 56, so 11 more lines of code I added to get the OpenMP one. And if I look at the threaded, this is the p-threaded version. 77. So from 45 to 77. So not quite double. I can diff the files. You can see what the files are. But the threaded program, if you've ever written a POSIX thread or a p-threaded code, there is a lot of work you need to do. You need to manage your threads. You need to protect your global variables. You need to fork and join your threads. It's a lot of, the whole application needs to be thread safe. With OpenMP, you can literally put a couple of directives in on the loops that you want to parallelize. And with Autopar, you do nothing. It's the exact same source code as the serial version. So we have different techniques that give you different amounts of parallelization. The more work you do with POSIX threads, complex program is hard to do, but if you get it right, we have tools like the Analyzer to help you get it right. You'll get very good performance when you're running multiple threads on a multi-core system. If you only have a little bit of time, or if you don't want to spend a lot of work, you can try the Autopar or the OpenMP approaches.